Hey guys, thanks again for watching these videos. So in today's video, I want to go over a geometric representation of a qubit that will ideally help you visualize some of the later concepts that we'll go over, like quantum logic gates, and basically all processes involving a single qubit. Now, there are ways to represent multiple qubits with a Bloch sphere, but it's a little different. So let's go over a single qubit first. So initially, we know that we can represent a wave function or a qubit, ket psi, as some alpha ket 0 plus beta ket 1. Now, we know that alpha and beta are complex numbers, some a plus bi and another a plus bi. Now, you may be thinking, hold on, that's 4 independent variables instead of 3. The a and then b of the I, and then the other a and b of the I. So that in those alpha and beta. So how are we able to represent that on a 3-dimensional sphere? Well, it all comes down to the relative positions of both ket 0 and ket 1. Let me break it down. So we can leave ket 0 and ket 1 where they are, but we can take the alpha and the beta, and what we can do is transform it into polar coordinates. So you may remember from calculus class, polar coordinates can be represented as some REI theta, or REI gamma, or whatever angle variable you want to use. Now, we can decompose both alpha and beta into that, so let's say an R0 EI gamma, and the beta as R1 EI psi, for example. Now, let me break it and show you this visually, which will help you. This is some steps down the line, but it will help you a little bit. So our next step is that we can represent the R0 and the R1 as cosine theta over 2 and sine theta over 2. This is just a way to parameterize both of these lengths that we don't know what they are, but we can parameterize them as some theta. Now, here's where the relative positions of ket 0 and ket 1 come into play. So you know how I said before how alpha, the angle of that can be represented as some like alpha, or EI, e to the I gamma, and the beta can be represented by like R1, EI psi, for example, which is how it's represented here. But what you can do is factor out this e to the I psi in your alpha term. And once you factor it out, this new position, this is represented as psi, but you can represent it as e to the I psi minus gamma. And then you can take that term and represent it as a new variable entirely. So that gives you this term. And a key point is that this factor term contributes no physical meaning at all. So we can essentially disregard it. And then the entire equation comes down to our wave function, ket psi, equals cosine theta over 2 of ket 0 plus e to the I, and in this case, they represent it as psi, but it's actually the relative, the difference in the angles between what we talked about earlier, times sine theta over 2 ket 1. Now this gives us enough information to accurately represent it, any quantum state vector on a sphere. And this is how they do it. Well, this is a physical meaning of what theta and psi actually represent on the sphere. It's important to note that the directly vertical line here is your ket 0, and the directly vertical pointing downwards state vector is ket 1. Now, in order to uniquely determine the position of any state vector, ket psi, this is how they do it. Let me zoom in a little bit here. That might be a little too much. That's better. So we can represent the sphere with 3 axes, x, y, and z. And those independent vector decompositions in each of those directions are represented like this. Vz is cosine theta, Vx is sine theta, cosine phi, and Vy is sine theta, sine phi. And this allows us to uniquely decompose every unique quantum state vector onto a sphere. That's the key idea. If you have a pure state vector, some alpha ket 0 plus beta ket 1, you can represent it as a unique unit vector on this sphere, with your vertical upward unit vector being ket 0, and your vertical downward unit vector being ket 1. And then anything in between those two vectors is some superposition of the two states. So yeah, thank you guys. Bye.